Hi, my name is Elise, and today I'll be teaching you how to complete an advanced functions sinusoidal application question. So the question is in the Nelson Advanced Functions textbook on page 372, number 10. The number of tons of paper waiting to be recycled at a 24-hour recycling plant can be modeled by the equation PT equals 0.5 sine pi over 6t plus 4, where t is the time in hours and PT is the number of tons waiting to be recycled. A. Use the equation to estimate the instantaneous rate of change in tons of paper waiting to be recycled when this rate is at its maximum. To make your estimate, use each of the following centered intervals. I. 1 hour before to 1 hour after the time when the instantaneous rate of change is at its maximum. II. 0.5 hours before to 0.5 hours after the time when the instantaneous rate of change is at its maximum. And III. 0.25 hours before to 0.25 hours after the time when the instantaneous rate of change is at its maximum. And B. Which estimate is the most accurate? What is the relationship between the size of the interval and the accuracy of the estimate? So I'll just read through the question one more time. The number of tons of paper waiting to be recycled at a 24-hour recycling plant can be modeled by the equation PT equals 0.5 sine pi over 6t plus 4, where t is the time in hours and PT is the number of tons waiting to be recycled. A. Use the equation to estimate the instantaneous rate of change in tons of paper waiting to be recycled when this rate is at its maximum. These images of paper recycling plants demonstrate that we are solving for the maximum rate at which paper is waiting to be recycled. What we are going to be doing first is drawing a sketch of the graph, then finding the point at which the rate of paper waiting to be recycled is at a maximum, and then solve for the change in this rate between the three time intervals given. First, we'll draw our base positive sine graph, which has a period of 2 pi, and it has zeros at 0, pi, and 2 pi. It reaches a maximum value of 1 at pi over 2 and a minimum of negative 1 at 3 pi over 2. Now we'll draw our function PT equals 0.5 sine pi over 6t plus 4, which has been compressed vertically, compressed horizontally, and shifted up 4 units. Now we're going to find the period of our graph using the k value, which is pi over 6. So the formula for period is 2 pi over k. So ours is going to be 2 pi over pi over 6, flip and multiply, 2 pi times 6 over pi. The pi's cancel out, and you're going to get 12 hours. So now we'll just draw the graph. Since the period is in 12 hours, we're going to complete one cycle in 12, 2 in 24. Our equation of axis is at 4, so at 0, 6, and 12, our points will be at 4. At 3, our point's going to be at the max, and at 9, it's going to be at the minimum value. The amplitude is 0.5, so our max point is going to be at 4.5, and our min is going to be at 3.5. We are trying to find the instantaneous rate of change in tons of paper waiting to be recycled when this rate is at its maximum. And we know that by looking at the graph, this point is going to be where the slope of the graph is the steepest. By looking at our graph, we can tell there are 3 places in one cycle where our graph is at the steepest. We have one here, here, and here. We are not going to use this place because the function is decreasing here. We won't use this place because of this would go into a negative value across the y-axis, and we will use this point. As you can see, the graph is very steep at this point. So the instantaneous point at which the graph is increasing its maximum rate is exactly at 12 hours. Now we're going to solve question I, which states 1 hour before to 1 hour after the time when the instantaneous rate of change is at its maximum. So we know the max instantaneous rate of paper waiting to be recycled is 12 hours. Therefore, our t value is going to be 12 minus 1, 1 hour before is 11, and 12 plus 1, 1 hour after is 13. Put those values in for t into your equation and solve using a calculator to get 3.75 for 11 and 4.25 for 13. Now we're going to do a slope calculation. PT2 minus PT1 over T2 minus T1. And you're going to get 0.25 tons per hour. Therefore, to put this into context of the question, 0.25 tons of paper are waiting to be recycled per hour. Next, moving on to question II, which states that 0.5 hours before to 0.5 hours after the time when the instantaneous rate of change is at its maximum. So our first t value is going to be 12 minus 0.5 gives you 11.5. And the next one is 0.5 hours after, so 12 plus 0.5 gives you 12.5. Now put those into your equation for t and solve for pt, getting these values. And again, we'll do slope calculation, pt2 minus pt1 over t2 minus t1. And you're going to solve that, and you are going to get a value, a rounded value, which is 0.2588 tons per hour. In the context of this question, this means that 0.2588 tons are waiting to be recycled per hour. Lastly, for part A is III, which states 0.25 hours before to 0.25 hours after the time when the instantaneous rate of change is at its maximum. So our t-value is going to be 12 minus 0.25 is 11.75, and 0.25 hours after is 12 plus 0.25 is 12.25 hours. And if you put those into your calculator for the t-value and solve for pt, you'll get these values. Slope calculation, pt2 minus pt1 over t2 minus t1. Solve for that, and you will get 0.26105 tons per hour. Again, this means 0.2615 tons of paper are waiting to be recycled per hour. Moving on to question B, which states, which estimate is the most accurate? What is the relationship between the size of the interval and the accuracy of the estimate? The estimate that is the most accurate is III at 0.2611 tons per hour, 0.25 hours before and 0.25 hours after. And this is because this is the smallest interval, so closest to the point of maximum instantaneous rate of change. What is the relationship between the size of the interval and the accuracy of the estimate? Well, as the size of the interval increases, the accuracy of the estimate decreases. Therefore, this is an inversely proportional relationship. Lastly, I will talk about careers in math, specifically for sinusoidal functions. So a possible career could be working for the Canadian Hydrographic Service. Working for the CHS, you would produce nautical charts about tides, currents, and water levels. When looking at tides, you would create sinusoidal graphs in order to determine times for high tide and low tide.